Welcome here. Another quick video. What are we talking about here? How about balancing equations? That sounds like a good one. Take up a few minutes of our time, perhaps. So, balancing equations, we use equations to represent chemical changes, chemical reactions. We also use equations for physical properties as well. So, let's talk a little bit about some of the parts of a chemical equation. On the left-hand side of the arrow, we have our reactants, which is our starting material. Our products are on the right-hand side. That is what is formed. And we use our formulas here for reactants and products. We also will sometimes see S, L, G, and AQ written next to formulas. This meaning solid, liquid, gas, and of course, aqueous. Aqueous is really a solution, and sometimes people wonder they're both in the liquid sort of form or they the same. The answer is there's actually a difference between liquid and aqueous. We're going to give you a quick example. If you had just pure water by itself, that is a liquid. Nothing else with it by itself. If you take water, which is a pure liquid, and you add something like sodium chloride to it, which is a solid, the sodium chloride will dissolve in the water, and that will make a sodium chloride solution that is aqueous. And aqueous is really a solution. It's a homogeneous mixture. And maybe in a later video, we'll talk more about a solution, but it has two parts. It has the solute, which is the smaller part, and it has the solvent, which is the larger part of a solution. By the way, in my example, the solute is the sodium chloride. The solvent is the water. How do you know what the solute is in a solution? Well, frankly, it's the name of the solution. So you got a sodium chloride solution, that's your solute. You got a potassium chloride solution, that's your solute. And if it's ionic, probably water is your solvent. It doesn't always have to be, but it probably is a good solvent for a lot of organic or inorganic ionic sort of compounds. I'll spit that word out. Ionic compounds like sodium chloride, potassium chloride, and so forth. Other things sometimes seen equations on top of the arrow, a little delta symbol usually means heat. You'll also sometimes maybe see like water written on top, which means maybe you dissolve something in water. And most of the time you'll see a catalyst written on top. A catalyst is not a reactant, it's not a product. It doesn't get used up in the reaction. It's there in most cases to facilitate the reaction happening faster, speed up a reaction. That can be something like a metal like platinum. It can be something like a acid, which is sometimes abbreviated as H plus as a catalyst. But again, sometimes those things are written up on the equation. So when we use an equation, it should always be balanced. There's probably no time in chemistry that if you have an equation, it should not be balanced. So it should always be balanced. So if you had something like this equation here, this is an unbalanced equation, and we would want to balance it. And when we balance equations, the only thing we could change are the coefficients in front. So those are the only things that we could change to balance this equation. You can never change the subscript, because if you do, then you kind of change what it is. If I take away that 3 from NH3, I'm no longer talking about ammonia. It's something different. So we never change the subscript. By the way, we never put numbers in between. That's a no-no. People like to do that by some chance. So only those coefficients. Now, when you balance equation, you basically want the same number of elements on each side of the arrow. And there's really only one or two major things you got to make sure of at the end. It is balanced. You have the same number of elements on each side. All the coefficients need to be whole numbers, and they need to be the simplest set. of whole numbers. So what do I mean by that? Well, I mean, for example, if I were able to balance an equation such as this, and again, we'll just assume these coefficients are balanced equation here. Although it may be balanced, I actually could go back through each of these coefficients and actually divide them by 2 and still get whole numbers. And that would get me to something like a plus 2b goes to 3c. And this would be the properly balanced equation. Now, sometimes, again, you can maybe see larger numbers and the equation is absolutely balanced. You have the same numbers of elements on each side. But if you have the ability to go through those coefficients and balance or reduce all of them down, not just one, but all of them down, and still get whole numbers, that's exactly what you should do. So we take our unbalanced equation like so. Just rewrite it here. Little sound effect. We don't have a big budget here, so just got to do a little sound effect. There we go. There we go. Now, personally, I'm a fan of tables when you're balancing equations. So if you look at this equation, no polyatomic ions involved. Might as well just lay yourself up a table. We got reactant side, product side, and these are the elements involved. So on the left-hand side, we got 2 nitrogens. Right-hand side, just 1 nitrogen. Left-hand side, 2 hydrogens. Right-hand side, 3 hydrogens. So here, the table kind of organizes everything. It tells you maybe where to start. I personally think you should start with what seems easiest to balance, and that's in one thing on each side. Here, nitrogen looks really easy. I could put a 2 here to balance my nitrogen. When I put a coefficient in, it does go for everybody behind it. So that would now give me 2 nitrogens, and 2 times 3 would give me 6 hydrogens. What usually happens when you go to balance equation? Well, you fix one thing and frankly mess up something else for sure. So we fixed the nitrogen here, but kind of messed up the hydrogen. That's not a problem because now we could go to left-hand side and put a 3 there. And now I have 2 nitrogens and 6 hydrogens. Just like that, I just balanced an equation. Everything looks good. Let's take a look at another one here. We'll do C3 H8 plus a little O2, a little CO2 plus some water maybe here. Once again, no polyatomic ions, so I'm just gonna make a table, reactant side, product side. I got carbon, hydrogen, and oxygen. So looking here on the left, we got 3 carbons. On the right, we got 1 carbon. Left, we got 8 hydrogens. Right, we got 2 hydrogens. Left, we got 2 oxygens. Right, we have 2 oxygens there. And we don't want to forget about this one over here. That's 1 more, which makes 3. Once again, here I'm going to start with, frankly, in my opinion, what seems super easy to fix to me and hopefully to you. Carbon looks pretty easy to fix. I could put a 3 right there. Once again, that is going to go for everybody behind it. That's going to give me 3 carbons, still 2 hydrogens over here. And now in terms of my oxygen, I have 3 times 2, which is 6. And I still have 1 more over here, which is now 7. Now I'm ready to balance my next element. I have a choice of hydrogen or oxygen. Here's my thinking on this. I'm going to go with hydrogen first because when I look at hydrogen, 1 spot here on the left and 1 spot on the right is hydrogen. What about oxygen? Well, here on the right, oxygen's in this thing and this thing, multiple spots, and 1 spot over here. So in this situation, because oxygen is in multiple things on the right-hand side and hydrogen is only 1 thing on each side, hydrogen is going to be way easier to balance. I would save the oxygen for the last. So to balance my hydrogen, I'm going to do a 4 there. And once again, that's going to go for everybody behind it. That's going to give me 3 carbons. That's going to give me 4 times 2 is 8 hydrogens. I still have 6 oxygens here, but now I have 4 times 1 is 4. And that gives me a grand total of 10. Now I'm ready. Well, let's see. I can now go to the left-hand side, and a 5 should do it for me. I now have 3 carbons, 8 hydrogens, and 5 times 2 is 10. That is a winner right there in terms of balancing. So again, kind of go back and forth. Everything should eventually fall into place. Take a look at maybe another one here. That's everything falls. So let's take a look and see what we got here. How about C4H10 plus O2 gives you CO2 plus water. So in this particular case, kind of a similar equation. So let's take a look. We got reactant, we got product, we got carbon, hydrogen, oxygen. Left-hand side, 4 carbons. Right-hand side, 1 carbon. Left-hand side, 10 hydrogens. Right-hand side, 2 hydrogens. Left-hand side, 2 oxygens. Right-hand side, 2 oxygens. 1 more gives me 3. Once again, here, kind of following the same pattern as last time. I'm going to start with what seems simple, and to me, that's going to be carbon again. So I'm going to go with 4, which goes again to everybody. So that's 4 carbons, still 2 hydrogens. I now have 4 times 2 in the first one, which gives me 8 oxygens plus 1 more, gives me 9. Here again, we're in kind of the same situation. I got oxygen in multiple things, hydrogen in just one thing. Hydrogen is my next stop here on the balancing train. I got 10 on the left, 2 on the right. I'm going to fix that by putting a 5 there. Going to go for everybody behind, and that's going to give me again 4 carbons. 5 times 2 is 10 hydrogens. I still have 8 on oxygens there, and now I have 5 times 1, which is 5. It's a lot of math there, but that's 8 and 5. I can go with 13. So now I've kind of filled in everybody over here. The only oxygen I got left is over here, and it's 2 of them, and I need to make it into a 13. So sometimes this does happen when you're balancing an equation. You kind of has to turn a number into a different number, and there's really not a whole number that will do that for you, perhaps. So this is where you can actually use a fraction to balance it. So how you use a fraction is the number up on top of the fraction should be the number you need. So let's see, in our case, we need it to be 13. So that's what I'm going to put up here on top. The number on the bottom should match the subscript on the formula. And in this case, our formula is O2, which means on the bottom should go at 2. Now, if I do that and use something like 13 over 2, I now have on the left-hand side 4 carbons, 10 hydrogens. And when I take 13 halves times the 2, which is the subscript, those are going to cancel and give me 13. And believe it or not, my equation is balanced. So you could absolutely use a fraction, and it happens like this. Sometimes when you have a molecular element, one of those diatomic elements, molecule elements by itself, and that element and other things on the other side, you sometimes have to use a fraction to balance it. So if you remember when I said at the beginning, all of our coefficients do need to be, though, whole numbers. So although you can use a fraction to balance it, you cannot leave it as a fraction. So we do have to take this equation and we got to get rid of the fraction. So to get rid of the fraction, you need to actually multiply the entire thing by the denominator, not just the fraction. So if I distribute that 2 across, 2C4H10 plus 13 halves times 2 is 13 O2s. 4 times 2 is 8 CO2s. And 5 times 2 is 10 H2Os. If we didn't mess anything up here, we should still be balanced. So let's take a look. We got 8 carbons there, 8 there. That's a good deal. So we got 8 and 8. So check. Hydrogen, we got 2 times 10 is 20. 10 times 2 is 20. So that's a check and a check. 13 times 2 is a lot, but we'll go with 26. Over here, we have 16 oxygens and 10 in the second guy. It looks like a 26 to me. And we are still balanced in this case. So sometimes you can balance an equation using a fraction. Again, number on top of the fraction, number you need. Number on the bottom should match the subscript. You just need to clear the fraction by multiplying by the denominator, and you'll have your balanced equation. Now, what happens if we have an equation that involves some polyatomic ions? So let's just say we had something like this. Well, magnesium nitrate plus, I don't know, let's go with a little sodium phosphate. Sounds like fun. And we'll end up with a little sodium nitrate and a little magnesium phosphate here. All right, so we have this equation and we want to balance it, and you look at it and go, well, it does look a little bit more complicated than what we've been looking at. So you could absolutely do what we've been doing, which is element by element, but there is a lot of kind of multiplying in and multiplying out that you need to do. And it can get a little bit confusing. So sometimes when you have polyatomic ions on both sides of the equation and they look the same, so we got nitrate on the left and right, phosphate on the left and right, it's better to keep those guys together as whole units and just balance them that way. So for example, here we basically have 2 nitrates on the left. We have 1 phosphate here on the left. Here we have 1 nitrate and 2 phosphates. So the truth here is you could kind of start with whichever polyatomic ion you want. Sometimes one will work better than the other, but if you start with perhaps the one that has, I don't know, sometimes the bigger positive or bigger negative charge, that sometimes works better. So that's what I'm going to do. I'm going to try the phosphate first. So here I have 1 phosphate on the left. I have 2 on the right. So to fix it, I'm going to put 2 in front of my sodium phosphate. That's going to give me 2 of these phosphate units. And where should I go next? I should actually go whatever it's attached to. So that's the sodium, and that's now 6 sodiums. That means I should then roll over here to sodium and put a 6. That 6 goes to the sodium, also goes now to my nitrate, and that's where I should go next, to the nitrate. Over here I have 2 nitrates. To get this guy to 6, I need a 3. That gives me 3 magnesiums, which actually fixes magnesium. And now gives me 6 of those nitrate units. And now I'm balanced. So as you can see, much quicker if you kind of keep those polyatomic ions together rather than going element by element. Probably also less chance of error, as you have less to sort of multiply in and out. One last thing here about balancing equations. If you have something like, we'll just look at this, just so if you did go element by element, for example, let's just make sure we count everything correctly. Let's just say we were looking at this guy. We were counting up what we had going on here. We would have to take this 3 and it would count for the magnesium. So we would have 3 of those. This 3 would also count for the nitrogen and the oxygen, but there's also a 2, which also counts for the oxygen and the nitrogen. So if we count up all that, we basically have 2 times 3, which is 6 for the oxygen, and then 6 times 3 is 18 for the oxygen. Here we would have 2 times 1 for the nitrogen, which is 2, and then 2 times 3 is 6. Because basically if we drew all that out, we basically have this magnesium, and we have 1 nitrate and 2 nitrates. That's basically what this formula is. But we also have 3 of them, which means we have another set of these guys and 1 more set of these guys. So that's what the coefficient means. We basically have this setup right here. And that's why we have to distribute in from the parentheses and also to the coefficient, because as you can see here, this is where we get our 1, 2, 3 for our magnesium. This is where we get for our nitrogen 1, 2, 3, 4, 5, and 6. And this is where we get for our, we'll go with this, our oxygen 3, 6, 9, that's a lot of counting, 12, 15, and 18 for our oxygen. So if you do have something as you're balancing, you have something with parentheses, you gotta, and a subscript, you gotta multiply in. And if you have a coefficient, you also have some multiply out. So again, if we were looking at this last one here, this 2 would go to the oxygen, which means there would be 8. This 2 would go to the phosphorus, which means there would be 2. There is no coefficient here, so no more multiplying than that, but that 2 counts for both of those guys there. All right, this quick video on balancing equations. Remember, if you got an equation, make sure it's balanced. For always look at it. If you see coefficients, most likely it might be balanced. You should really take a double look at it. If you see no coefficients, you should take a really hard look at it. Thanks again for watching. I hope this helped. Again, any other topics you want to know about, just let me know in the comments. Otherwise, guess we'll catch you on the next one. Bye-bye.